Any questions? Yes.
This isn't about the physics, about the schedule for this week. I can't read from what is happening this week.
Equipotential lab due.
Just tomorrow.
Yeah. Other questions? Go. I have a 3 nanocoulomb charge bathed in a constant electric field of 4 newtons per coulomb. Sure, why not? What is the force acting on the charge?
12 newtons.
Pardon?
12 newtons.
Close.
Oh. It's something with the nano, but I can't figure out how to convert it.
Yeah, just throw the word nano in front of the unit.
Nanonewtons?
Yeah, nano. Or 12 times 10 to the negative 9th newtons, or something like that, but let's not forget the nano there. All right, so in this case, the force Q E, and so 3 nanocoulombs times 4 newtons per coulomb, and you end up with 12 nanonewtons. All right. If so I have a constant electric field, and let's do a little bit more basic than that because it's chapter 19. I have a 10 meter by 10 meter plate. They both are. I hook it up to a battery. I've done this spiel about battery versus power cell. So Ibrahim wasn't paying attention. Anyone else? All right, so this is the symbol for a battery. This is the symbol I use for a battery. Now, I've had only one student sort of have a problem with it, but from purist point of view, this technically is not a battery, it's a power cell. Now, a battery is composed of more than one power cell. So properly, a battery should be listed as at least 2 of them. Sometimes you'll see 3, and occasionally I'll see 4. But I'm going to be using just a single one to represent the battery, or some sort of direct current power supply. So if you later on are talking to somebody who deals with this stuff and you do this for the battery, they might roll their eyes and look down upon you, but just recognize that they're picky about something I'm not.
So,
either of you.
Is that drawn almost like the top of a vector symbol?
There's supposed to be 2 straight lines, segments.
Just at the bottom.
2 straight lines like this?
Yeah, except one's bigger than the other. Does that answer your question also, Jack? All right. Now, because this is direct current power supply, it has a certain voltage. So think of battery. I got a 12 volt battery, then there'd be 12 volts between the 2 leads. If you recall, looking at a battery, there's a positive side and a negative side. In the case of the batteries with the little cap right there, it'd be a positive side has the cap, the negative side does not, at least in all the batteries I've seen. When I'm writing a plus sign, I use twice as much ink than if I write the minus sign. And I assume the same is true for you. The one that requires more ink is the positive side. So that's the positive side, positive side, and that's the negative side.
Can they be reversed?
Yeah. This just means I have the battery set in like that. That's a simple purple. I can't draw them sideways apparently. Now, on a battery, got a positive and negative side, so there's usually some barrier in between. For the rechargeable batteries, you can force electrons through the barrier, but every time you do that, it weakens the barrier, so that at some point, rechargeable batteries won't recharge anymore because electrons can flow freely. And if you have a bunch of electrons flowing freely to the positive side, you neutralize the whole thing, and you basically have a paperweight or landfill. We got a bunch of electrons here, and a bunch of protons here, and they want to get to each other. Again, because of the barrier, they're not going to do it. So the way that you can get them there is if I take a wire or some sort of connector and I connect one to the other, I now have a path for them to take, so that the electrons can now start flowing through the wire. Now, it takes a while for an electron to go from one side to the other.
How long is the wire?
It really doesn't matter. They travel along the wire in a couple centimeters a second. And this probably should not be used on this board. So if you think about a I have a long wire here, and this is connected to some reservoir of electrons, and this is connected to some reservoir of protons. The electrons are the ones that are going to move. If you think about it slightly differently, I've got a bunch of electrons. I mean, this is composed of atoms, and I've got a bunch of electrons in the electron sea that can move. And this electron is going to say, oh, I got a positive charge there, let me go. I've now created a hole. That hole is going to be filled by that electron, and so the hole is now here. That electron goes here, so the hole is here, and so forth. So the hole is moving in that direction. The electrons are moving in the other direction. So the electrons move this way. The hole moves that way. Now the H plus is not an actual particle. It is just sort of the illusion of a positive charge traveling to the left.
Now,
I have seen this notation before in referee journals. I mean, this is legitimate notation, but just recognize this represents a hole, not an actual particle.
I don't know if this actually matters, but the hole, it probably doesn't last very long, right?
Right.
I was just asking.
That's that, yeah. But all I need for current to flow is I just need electrons flowing. I don't need an electron to go from here all the way over to here. I just need an electron to move. Now, when they first were coming up with current, this idea of current, I guess Ben Franklin was picturing water flow and pictured some sort of positive fluid flow. So even though the actual particles that are moving are to the right in my diagram, the standard that was set up is that current flows the opposite direction. The symbol for current is an I. This is current. And the current flows in the direction of the hole. It flows in the direction of, if I have positive charges moving, positive charge flow, or opposite the direction of negative charge flow. Now, I do get positive charge flow if I've got, say, a high energy experiment and I take a bunch of hydrogen atoms, strip off the electrons, so I got a bunch of protons, and then I shoot the protons at a target. I got positive charge flow then. Probably in all of your experiences, current just flows opposite direction of the electron flow. Other than physics 152, where occasionally we will have positive charges flowing. Does it count as a flow if you're shooting it? Does a bullet flow through the air? So, over there, I know that I have electrons coming off the right side and going into the left side. So I have electrons flowing this way, now that they have a path, and flowing in this way. Well, I've got two plates here. An electron's going to come along, and the first electron's going to get to the plate, no problem. When the electron shows up here, I have an electron flow off of that. So every time I have an electron flowing here, I've got one flowing off on the other side, assuming that these are close enough together. I get another electron over here, I have another one leave over here, and so eventually, over time, I get a bunch of electrons coming on this side and leaving this positively charged. And so that on one plate, I've got a positive charge, the other plate I have a negative charge that are just equal in magnitude, opposite in sign. Not opposite direction, because that would imply a vector, and these are not vectors. So, how much can I put on this? How much can I put onto a plate? Well, it depends upon the capacitance. So let's introduce yet one more word. Capacitance. Capacitance is a measure of how much charge can be stored per voltage. The symbol is a C, capital C. Do not confuse that with coulombs.
You just ran out of letters, right?
Yep. And that is equal to the charge that's on the plate divided by the voltage between the plates.
Voltage and not volt, right?
Correct. So if I have a potential difference between the plates of 12 volts, I get a certain amount of charge sitting on them. If I have, if I double that, well, I get twice as much charge for the same configuration.
So I know at the beginning of the class, well, at the beginning of the semester, you said you use the little q and the big Q interchangeably.
Yeah, mostly.
Is that still the case here, or?
It's not, since we're talking about capacitors, a capacitor, you probably aren't going to have a single charge on it.
Okay.
Yeah, you probably would not notice if I just had a single charge on it. So capital Q is appropriate here.
Question about the diagram. These two walls, is there just like an opening in the middle, or are they connected, or like what's going on?
If they were connected, charge would flow right through them. So there's got to be there's a gap there. Now, we can make the gap smaller. Obviously, if I take two metal plates and I put them really close to each other, it'd be very hard to keep them separated. So we can keep them separated by sticking an insulator in between it. Now, the insulator you stick in between it is also known, in this case, as a dielectric. So if you see the term dielectric, think insulator. So we will get to dielectrics before we're done today.
So in this diagram, it's like you have a sheet, or you have a battery at the bottom, then you have a piece of paper, a 10 by 10, like metal thing coming up like
Right.
this. That's what we're drawing.
You know what? Pause this. There's enough dead space in my videos already. All right. A capacitor could be as, this is known as a simple form of capacitor. A capacitor. You just hook the leads up to a battery, put the plates parallel to each other, and hey, you can store charge. It's as simple as that. We can get them closer by taking an insulator, putting it in between it, and then pressing them together. Just so long as the plates are not touching. And so the closer they are, the better the capacitor will be. The more charge that will be.
Can you move the box?
Your X-ray vision not working today? So that is a simple form parallel plate capacitor. Now, if I take my parallel plate capacitor and have a more flexible material there, if I roll it up, I still have a capacitor. Then you get something like this. This is also a capacitor. This one I think is shot, but I haven't tried charging it.
So if you just took the metal and you turned it, and you bended it to be
Yeah.
cylinder.
So you take your aluminum strip, stick a plastic in between them, and then roll it up.
Okay.
Then I didn't roll it up particularly well there, but it's much smaller space. I think that's what you were asking.
Yeah.
Okay.
But that's how it's done, is that they take it and they literally just fold it so it's multiple layers
Yeah.
of it. So, okay.
Yeah. That's the simplified form. Now they have more sophisticated ones at this point, but that's the essence of it. Other questions? All right. One other concept to introduce. Well, or actually, introduce or reinterpret. We talked before about the difference between electric potential and electric potential difference. So if I have, let's say, 12 volts there compared to something, 6 volts there, 3 volts there. If I start from 12 and go to 6, what is the potential difference? If I go from 12 to 3, if I go from 12 to 3 to 6,
Back to negative 3. I mean, negative 6.
negative 6. If I go from 12 back to 12,
0.
all right. So if I start here, imagine I got a path here. I start here and I end here. So in the exact same spot. What's the potential difference between this and itself?
0.
Let's throw units in for fun.
Volts. 0 volts.
Okay. That is the essence of what is known as Kirchhoff's voltage rule. And now my annual, did I spell it right? Moment. I think they're 2 inches, but that doesn't look right. It's gotta be written down someplace.
Yep, 2 H's and 2 F's.
All right. F I was more confident with. All right, so Kirchhoff's voltage rule also known as Kirchhoff's loop rule. And it says that if I start at any point in a circuit and I go all the way around the circuit, all my potential gains and potential losses will add up to 0. So I start here on the negative side and I go to the positive side. I could go the other way, but I want to go this way. So if I'm going from negative to positive, do I have a potential gain or a loss? Yeah. So I gain potential going from negative to positive. I'm cruising around. I'm going to cross over my capacitor here and then come back to where I started. So if this is a 12 volt battery, I gain 12 volts here. What's happening here?
Losing 12 volts.
Yeah. So if I gain 12 there going along my path, I'm going to have to lose 12 going that way. And again, similar to the battery, in the battery I've got, when I go from negative to positive, I gain. Here, if I'm going from positive to negative, I lose. Same true here. If I go from negative to positive, I gain. Positive to negative, I lose. Either one. The direction of the loop matters. Sorry. Once you start in a direction, it does matter what you do the rest of it. You have to end up back where you started.
Now, if there was something cut off, what happens?
Cut off, as in there's a break in the wire.
There's a break in the wire, there's a break in the current.
If there's a break in the wire, if there's enough of a gap, then current stops flowing. If they are really close to each other, you get sparks potentially, if the potential difference is large enough.
But wouldn't the green circle break? Or what?
Yeah, that when you're doing a loop, you have to do you actually have to do a loop of components. So if I have a break here, then that loop doesn't exist anymore.
Oh, okay. So for example, on the test problem, like we'd be asked to draw that out. We have to make sure it matches up with what's on the equation. See what I'm saying?
My gut says yes. And it depends on what you meant.
Yeah, just being able to like to draw and understand the correlation between each one of the.
Yeah, where the potential gains are and the potential losses are, yes, I will be expecting that to happen.